Hi everybody and welcome to this tutorial. So this is Clotilde Pierson from Oregon State University, and today I will show you how to run spectral simulation through the image-based template from Lark 2.0. Lark 2.0 is a collaboration between Birta Carintazzi Mazzuti from Eindhoven University of Technology and myself. And it is basically just an update to Lark Spectral Lighting. So let's start from the Rhino 3D interface. As you can see, I already have a 3D model of a simple room. That's the room that I will be simulating. And so let's directly call in Grasshopper and load the image-based simulation template. So that's the one that I want to show you now. Okay. So in this image-based simulation templates, let's zoom out so that I can show you the process, which is very similar to the point-in-time simulation template if you already watched that tutorial. So we have 4 parts of the simulation, the first one being the inputs, and we will see that in details just after. Then you have a second part where you can start running the simulation, several steps here. You have the actual process of the spectral simulation, image-based. I will go over these to explain you quickly the general overview of this process later on. And then at last we have the outputs on the right from the simulation. Let's start with the inputs then. So today I want to run a simulation using both daylight and electric lighting, so that's correct. So basically what you have to do is simply follow all the steps that are described here. So first, defining what are the light sources in the scene. We want to run a simulation with both daylight and electric light, so we will select both. Then we need to define the camera view. So because we are doing an image-based simulation, we have to select the view of the camera that we want to simulate. So this is a bit different from the point-in-time simulation, from the grid-based simulation. And basically, this small code actually reads the named view that you have saved in Rhino. And so if we go back to the Rhino interface, you can actually see these 3 views are mentioned here. So right now I'm in the perspective view, and so if I do run the simulation now, I will get this view that is simulated. That is not what I want, but I have actually already saved 3 views, and the view that I want to simulate today is the test view 1. And so I can just go back to this first test view 1. It appears here. So I go back then to Grasshopper. I need to rerun this component, and you can see that now the test view 1 is appearing, right? So it always reads the 3 viewed names that you have here. And so in these view names, named views, I just need to select the one that I want to simulate, and in this case it's indeed the 0 index. Second thing is setting up the daylight inputs. First, the time of the year that I want to run the simulation. In this case, I will run it for, May 27. Well, let's keep it at 4. Then I can decide whether I want to input directly a weather file, and I will include here the web link where you can actually download this ipW weather file for different places around the world. I have actually one such weather file that I want to use. And so I will go here. The other choice that you have is, instead of using an ipW file, you can directly input the data that you want to simulate for. And so all this data you can actually input there, and then you would just need to set this component and override the ipW file to true. The last input for the spectral sky model is obviously the spectral information. This is given through the sky spectral power distribution, or sky SPD. In the case of Lark, only the diffuse part of the sky is spectral, and the sun will be simulated as a white light source. And by default, the diffuse sky SPD is set up to a D65 illuminant, and you have all the values of that illuminance that have been implemented here. If you want to change that, you can do it there. And this second component just gives the spectral resolution. So if you change the diffuse sky SPD in the first one, you would need also to make sure that this corresponds to the right wavelengths in this one. So that's for the sky. Then we can zoom in on the electric light inputs. The data that we want to input in this case are, again, the spectral power distribution of the electric light source. I already have one such file that I can upload. Oh, that's not the right one. Here, SPD text. That I can upload here, and I can show you what it actually looks like if I go to desktop simulation inputs. And so here you can have a look at this file, and so we have the wavelengths on the first column, and then the value of the spectral irradiance data. So that's for the SPD of the electric light source. We also need the IS file. I also have one such file for the electric light source that I want to simulate, which is a fluorescent light, and that's why I named it FL. So these IS files are typically provided by the manufacturers, so this one is easy to find. For the SPD text file, however, it is typically not provided by the manufacturer, but you could either measure it, or you can also find it maybe online. There exist some online databases of such data, and I will put the web link to one just here. And so we also need to set what is the wavelength interval in the SPD. In this case, it was 1 nanometer. The light loss factor, which is basically the ratio between the actual output of the luminaire and the theoretical one, which is described in the IS file. Typically, I use 0.8, but we could set it up to 1 so that we have the theoretical values when we simulate. A name for the electric light source, the Rhino layer where it is, and we also need to give that information here. So manually you need to also input the name of the layer, the Rhino layer, in the pipeline. And so that is the component that will go and pick up the geometry from Rhino. And then last but not least, regarding this luminaire, we can also rotate it. And then we also need, obviously, to input the materials spectral information to run the simulation. First, the material tab. We can choose between two main tabs. The first one is 0 for the glass or glazing, and the second one is 1 for plastic. This first material, as you can see, is the window, so basically the glazing, and in this case we will then use 0. And we need to input spectral transmittance information for this glazing. The spectral transmittance is typically inputted through a USR file. and so that's the one that I'm reading here. These USR files are the direct output of a free software which is called Optics version 6, and that is provided by LBNL. And I can also give you the link here, but basically you can build your own glazing unit and then output the spectral transmittance information for that glazing. And I will quickly show you what the USR file looks like. So you have the wavelengths and then the spectral information. So that's for the glazing. And then what other information do we need? The wavelengths interval again. USR file, typically it's 5 nanometers. The rhino layer, and then again here the rhino layer. The other materials are the opaque material. So in this case I had the walls, and so I just inputted the SPD of the wall. So again, this spectral reflectance information, you can input some information that you previously measured, but you could also retrieve such kind of information from online database, and I will also put you a link where you can access such spectral reflectance information. And these files, just to show you what format it is in, so we have the wavelengths again on the first column, and then the spectral reflectance information in the second column. So that's for the opaque material. In this case, as you could just see in the file, we have a 10 nanometers interval. Then we could also adjust the roughness and the specularity of this material. We need to input the rhino layer index and the rhino layer name in the pipeline. And so we do that for all the materials, and I will quickly change the path to the SPD information for these materials so that I can run my simulations. Okay, that's it. And then last but not least, we have the simulation parameters. If you don't know how to adjust these, I would like to refer you to either the Radiance online forum or the Radiance book, where you can learn about all these parameters and what they typically do. In this case, I won't optimize the parameters for accuracy, but I just want to have a simulation that runs relatively fast. So with that, I have set up all my inputs, and I can go to the second section of this template, which is the running the simulation. And if I actually zoom out, you can see that all the materials that were red when I first opened the templates are now gray, because they have the right inputs available, and so these are ready. What is still not ready though is this part as well as this part. And what are those two? Well, this one is the spectral sky model, and this one are the spectral luminaires for each of the 3 channels. And so that's the first step that we will need to do. We will need to write the light source files. If we toggle this component to true, we will create the spectral electric light source files and the spectral sky file. And so that's what I will do just now. It typically runs very fast, and you can see that for the spectral sky it becomes gray, as well as for the spectral luminaires. So I'm now ready to run my simulations, and that's what I will do here. So I just need to start this button, turn it to true, and it will launch the simulation. It will open a terminal window for each simulations that it runs. And basically you can see as if you would run a radiance simulation, the command line that you would use, and you can see that it's calculating, and it will pop up several windows, such kind of terminal windows for the multiple radiance simulations that it will run. Okay, so we just finished, and before turning on the last one, I just want to show you or to explain to you quickly the process that it goes through. So if we look at the process section, we have actually two columns. The first one is to process the inputs to the simulation and transform them from whatever spectral resolutions they are into a 9-channel resolution. And then the second column is for the 3 radiance simulations. So Lark and Lark 2.0 actually simulate or do run spectral simulation in 9 channels, and that means that they in the background 3 radiance 3-channel simulations are conducted, and so one for the blue channels, one for the green channels, and one for the red channels. So these are the 3 radiance simulations that are running in the background. And so for each of these radiance simulation, we have the inputs that are available here, right? And so we do that for all the materials. We do that also for the electric lighting, although this is done directly into the IES file, so it is not apparent here in the template. And then at last we do that also for the spectral sky model. And so here we have, and I can zoom in, the 3 spectral sky definition that we will use for these 3 radiance simulations. And so these elements are just processed by some original Lark components. So these 2 components, this one and these ones, what they do, well, this one is the one that typically reads any kind of spectral information and transform it to a 9-channel output. And then this one specifically deals with sky models. So that's what we use to define the spectral sky in this case. Again, here we use the same component to derive the 9 channels output for the electric light sources. That's the one. Here we deal with the view sensor, and so we define a bit more which camera type and simulation type we want to run, including the image pixel resolution. And then at last, the materials definition, which also use this original Lark component. And so with that, all of these elements or post-process inputs are set up in the simulation, which is a typical Radiance through Honeybee simulation, where you have the geometry and materials, the parameters that are set up here, the electric light source that can be added here. And this simulation, this is the component running the simulation, will output, since it is an image-based simulation, a luminance file, basically an HDR image, high dynamic range image. And so this HDR image, we can either read it directly, and that's what the typical or the original Lark simulation would do. So they are linked directly to the output and merge into one final or several final HDR image. One option that is offered through Lark 2.0 is to apply what we call directionality weighting, and I will go back to here to show you a bit more about this. Recent literature has shown that different parts of the field of view have somehow a different sensitivity when we talk about the ipRGC influenced light responses. And so there are weights that have been developed for these different parts of the field of view that can be applied to an HDR image so that we can calculate a more accurate representation of what our eyes and our non-visual system actually perceived in this context of non-visual responses. And so if we toggle this to true, we will actually apply the weighting factors to these images, HDR images, and then I will show you what it gives as outputs. And so basically this last part, the field of view weighting, is actually implemented here. And so you can see directly this component is the one that does the job. So once you have run your simulation, whether you want to apply this weighting or not, you will access your outputs and the results of your simulations in this last part of the template. And so there are two main outputs that we can read. The first one are HDR images. And we can directly look at those using the Ladybug image viewer. So this component, which is one of the original components from Lark, gives you as an output the path to these HDR images, as you can see. And so I can just connect that to the image viewer and I have the image appearing here. So that's the first one. I can show you probably the second one. Sorry, viewer. Here, so this one, so you have typically 3 HDR images that are outputted. The first one, the Sir Lucas peak, is an HDR image for which each pixel displays a luminance values, which is a circadian luminance value, so weighted with the melanopic curve from Lucas et al. The second one is a typical HDR image, including color information, so that's the photopeak color peak. And then the last one is, again, similar to this one, a grayscale image of which each of the pixels represents the photopeak luminance values. And as you can see, these are not like typical 180-degree field of view. So these are the field of view to which we have applied the weightings that I just explained. If I don't want to apply the weighting, I can actually go back and turn this to false. And in this way, I can see what would have been the outputs that I would have from the original Lark simulation, image-based. So that's the first output that we can get from this template. The second output is, again, the CIE toolbox. So basically from this HDR image, we read the irradiance, and then we apply the alpha opic framework that was developed by the CIE, where we can choose which alpha opic curve we want to use. In this case, we decided to go for the melanopic one. And then this toolbox will give us for that specific field of view, and based on the simulated image, the melanopic EDI, the melanopic ELR, and the melanopic irradiance. On top of that, we also output the spectral irradiance that you can actually read here and which is displayed here. Since it is a 9-channel simulation, we will have a step function as the output of this image-based simulation. Maybe I should just also mention that for this melanopic EDI, the weighting also applies, right? And so it calculates these values based on the image that you can observe here. And so in this case, there is no weighting applied, and we have a melanopic EDI of 1475. And if I go back and apply the weighting again, and it typically goes quite fast to apply these weightings. you can see that I have quite some difference in the melanopic EDI that is calculated, because I'm here now with 2200 lux of melanopic EDI. And with that, this is the end of the tutorial for this template. Thank you for listening, and again, I wish you very productive and successful spectral simulation with Lark 2.0.